Okay, so the main point on this whole thing in electrolytic solutions, these would be systems. Again, they're not at equilibrium, and they're very, very far from equilibrium. And even thinking about the standard cell potentials, all of the concentrations were at 1 molar. Okay, those produce what we call ionic strength solutions that are off the charts. Most of our equilibrium chemistry is based on really dilute solutions. And so we have this difference between the thermodynamic equilibrium constant and the concentration equilibrium constant. And so this is the key piece right here. That remember the equilibrium constant we said was an approximation to these species, these concentrations. Okay, that the real one was the partition functions. You remember that from earlier in the course? And that concentrations were kind of a stand-in for that. They worked pretty well, but if the solutions got too concentrated, then that assumption started to fail. And so we needed to take into account these activities. And so we really aren't able to get to the partition function. We just throw a coefficient in front of the concentration. Okay. And now in aqueous solutions, those coefficients can be greater than 1 or less than 1. So they can make the concentration seem larger or make it seem smaller. And so in this case, I'm showing this equilibrium constant and how it changes with concentration of salt in solution. So if we get down here and look, this is concentration of sodium chloride. And as the solution gets saltier, look what happens to the acid dissociation constant, which we have as 1 times 10 to the minus 14. It starts to move up, and it moves up dramatically. Okay. So what this tells me is that the more salty the solution, the more water breaks into acid and base. That's weird because sodium chloride isn't a pH active thing. Like we're not making sodium hydroxide, or we're not making hydrochloric acid. We're just making more acid and more hydroxide from water if the solution is more salty. And so that's the conceptual thing that I'm trying to point out with this lecture that's on Blackboard, okay? Is that the more salty the solution, the more stable the ions. Okay, so you can write that here. It says, ions in solution help stabilize other ions in solution. So this is the main point here. And so if you have a really salty solution, meaning your ion concentrations, your aqueous ion concentrations are strong, they're really high, then you need to calculate the ionic strength, and you need to use activities, not concentrations. And this lecture goes through the ramifications of that. So we redo a little bit of the equilibrium chemistry, but we put in these activity coefficients. And so there's a couple of ice table calculations, and we use these activities. Well, where do we get the activities? Well, we can calculate the activity coefficients using this Debye-Huckel equation. And all of the constants are labeled there. Or we could look it up in tables. And in this table, we have this hydrodynamic diameter. And so let me just mention that, and then we'll be done. This is sort of how the ion distorts water. Okay. So I don't know how to describe this in ways that you can think, but think about the sort of the cage around an ion. If it's got like an aluminum 3+, okay, that's a huge charge, and it's going to have water that's really attracted to it with the hydrogens pointing. I mean, the oxygen's pointing towards the 3+. And now there's a little ball of the hydrogens. And so then that's going to have another outer ring of water that's associated with those hydrogens. So how big is this ball before it's just random water? See, it's not the diameter of the ion itself, it's the hydrodynamic diameter. It's the entourage of water that's going with it. So you can think of, you got me walking in a room, no entourage. You got, I don't pick a famous person. I don't now Taylor Swift with her era, tour. She walks in the room, bigger entourage. Her hydrodynamic diameter is enormous, and mine is basically me, right? So that's what's going on. You have a really super big charge on an atom, like a Mg2 plus, a Be2 plus. Those are going to behave the same in solution because they're 2 plus. But isn't it weird? Lithium cation, and this is like benzoic acid. That's a huge molecule, benzoic acid, but it has the same entourage as lithium ion. Okay, neither one of those affect water very much because you got this big organic molecule with this tiny little charge on the acid piece. So those are the concepts in this. So go ahead and watch this video, and we'll be caught back up with the course. Okay, and to bring your questions next time.